seminar series is sponsored by the National University Rail Center here at the University of Illinois at Urbana-Champaign. And on behalf of all of us, we thank the USDOT for their ongoing support. It is greatly appreciated by those of us here on the campus, as well as those of you participating via the internet. And I'd like to welcome those of you who are participating via the internet, and just mention that we have participants from Montana Rail Link, ENSCO, TUV Rail Sciences, Illinois Department of Transportation, Benesh Engineering, Amtrak, the FRA, Vost Alpine Nortrack, Patrick Engineering, and a variety of other individuals. We are very glad that you could join us this afternoon. So just a little bit about the speaker, the topic of today's seminar and the speaker. Despite over 100 years of experience with use of concrete as a material for railway crossties, much remains to be learned. This is due in part to the increasing demands of the track structure, subjected to both heavier axle loads and higher speeds of modern rail operations. But more fundamentally, the requirements for material and structural design procedures or properties under a variety of conditions are still not sufficiently well understood, as witnessed by field failures thought to be related to harsh environments that inspired this research. Our speaker today will discuss a joint project with Kansas State University that was sponsored by the FRA, investigating the concrete manufacturing, mixing, and handling procedures, with particular emphasis on the effects of vibration. Research yielded insights that have led to new recommendations for precast concrete manufacturers that can improve the quality control of concrete ties. It's both a personal and professional pleasure to introduce our speaker today, Professor David Lange, who is a colleague of mine here in the Civil and Environmental Engineering Department and an important contributor to the RailTech program. He completed his BS at Valparaiso University in Civil Engineering in 1981, his MBA at Wichita State in 1984, and his PhD also in Civil Engineering at Northwestern in 1991. He joined the UIUC faculty in 1992 and is a Narby Kachaturian faculty scholar, and also serves as the director of the Center for Excellence for Airport Technology here. He is a fellow of the American Concrete Institute and the American Ceramic Society. He currently serves as the chair of the ACI Technical Activities Committee and is a director on the ACI Board of Direction. He formerly served as associate director of the Center for Advanced Cement-Based Materials and remains active in ACBM research activities. Dr. Lange was a recipient of an NSF Career Award and has been recognized for his excellence in teaching in Illinois. And speaking of that, he's going to have to leave right on the dot just before 1 because he has a class, so he's a responsible faculty to this day. In 2011, he won the Stanley H. Pierce Award from the University of Illinois College of Engineering in recognition for his efforts to develop empathetic student-faculty cooperation. Please join me in welcoming our speaker today, Professor David Lange, who will present the William Hay Engineering Seminar entitled Freeze-Thaw Durability of Concrete Crossties.
Okay, so the sound was off. Sorry about that, anyone online. And so catching up here, I'm giving it the motivation of this project as a FRA-sponsored project with the Broad Agency Announcement Funding Program. And the project brings into partnership Kansas State and the University of Illinois. Kyle Riding and I have known each other for quite a few years, but we had not previously worked together, and this was a great opportunity to team up. I also mentioned in the title Professor Randy Ewalt from Mechanical Engineering here on campus, and his contribution to the modeling, the theoretical modeling of fluid mechanics was was very helpful. You'll see some of that here today. The two U of I students who are most involved here are Dan Castaneda and Jeremy Koch. And there were other students involved as well, but those are the two PhD students who were involved in this research. So a few opening words about freeze-thaw durability. Here you see a concrete tie, half of a tie that was exposed to freeze-thaw cycling, much like our ASTM C666 test. It's 300 cycles of freezing and thawing, and you can see this kind of distress in concrete that's particular. This is a very poor performance, so this is, you know, as bad as it can get. And this arises because we have a microstructure of concrete that is permeable. It's a porous microstructure. It holds water. During freezing and thawing, we get the expansion of water and the development of stress that leads to cracking. And so we then realize that damage under freeze-thaw conditions requires something near saturated conditions. If the concrete was completely dry, there would never be any motivation for this concern. But we have this porous microstructure that can draw water in from its environment. So one of our questions early on was, can a concrete cross-tie be critically saturated in well-draining ballast? We see the infrastructure of rail is up on ballast. Why would we really run into saturated conditions? Isn't water just kind of freely moving away from this material? A second thing is, how many cycles does this tie actually feel? Because we know that this is not just occurring in one cycle of freezing and thawing, but it's a progressive kind of a damage that needs many, many cycles of freezing and thawing. And these questions about microstructure, about the moisture condition, about the climate, actually how does it impose on the material, really very little data, very little measurement on these kind of things. So that's what the project was about. Well, we know that concrete is intended to be freeze-thaw durable. And we have a main tool to do that called air entrainment, where we intentionally infuse billions of small little tiny bubbles that reside in the microstructure. Here's a picture of typical air bubbles from air entrainment. And the concept goes that we want the water that exists in the very, very fine capillary pores of concrete material to have a bleed channel, a relief channel, moving toward this air void. So this channel, this boundary, is a boundary with an air void. The bubble is, you know, huge, way beyond the size of the screen. And so if there's water inside these capillary pores that wants to turn to ice, that pressure can be relieved if there's a path outward. And by having these little air bubbles present in the microstructure, we essentially give that kind of pressure relief. That's the basic idea. And of course, the people who are involved in manufacturing concrete ties, they know this, and they input the air into the concrete. And so presumably, this would be taken care of, we would hope. But in fact, what drove this project in the first place is concern about field performance of concrete ties and an broad experience through the industry that when we expose our products to ASTM C666, the freeze-thaw testing, we do not pass it routinely. We continue to have challenges in passing these kind of thresholds for freeze-thaw performance. Why is this? So that was what motivated the project. Here's a diagram, a picture of microstructure to give you a little background about how we measure these things. And this particular picture shows how we're using a flatbed scanner and we're dyeing the paste surface with this pink dye, and the orange bubbles are illuminated, and we can get a scan of microstructure that gives us three phases: the aggregate, the gray in between is the paste, and then the white is the air bubble. So we did thousands of these images to characterize many, many different samples.
I never knew concrete could be so pretty.
Oh, it's beautiful. Okay, so our goals in this project were to improve the understanding of, first of all, how air bubbles respond to vibration during the manufacturing process. What are the actual conditions of the cross ties in the track? How we should produce ties with better freeze-thaw resistance. And then last, how new testing methods might assess freeze-thaw performance. These are kind of the global driving forces behind the project. We happen to have completed this project. We did our final presentation to the FRA in January, and I just wanted to mention a little bit about how this was organized because it gives you a chance very quickly to see how there was a significant contribution to theory, where we're talking about bubble mechanics and vibration and so forth. And then there was a section on the interaction with the manufacturing process. We spent 3 trips going to manufacturing plants, the team did, and 2 of those trips were a month long, so they were getting lots and lots of data. And then the last is a big initiative having to do with measuring things in the field. So it's kind of comprehensive in that regard. I want to start some remarks with kind of an overview of the rheology of concrete, because when we're talking about fresh concrete, the manufacturing of concrete products, we are concerned about rheology. And this is a standard curve that describes the stress-strain rate behavior that describes the flow of fluids. When we have a linear behavior that's marked Newtonian, that doesn't have any, we start to yield the material as soon as we apply the smallest of stresses. This is a fluid that might be something like water. There's no particular yield stress. But we have these other fluids that are Bingham behavior fluids, and they have some kind of stress, yield stress, that must be overcome before we strain the material at all. So you can think of this as a kind of a fluid that you need to apply a force, and the first low level of force does not move the stirring stick or the stirring rod, but once you surpass that, then you can start to shear the material. Okay, yield stress, and that is how we understand concrete. It's well known that concrete as a material exhibits Bingham behavior. And viscosity is measured on these charts as the slope of these lines. Okay, however, that's not really where we're having our problem. These measurements are made at basically static conditions, very, very slow yield. We're not moving the fluid at all. When we are vibrating the material, the behavior is different. So we can do these kind of rheological tests under vibration, and we get a different story. And the story basically is that we get near where we expect to have yield stress, that yield stress is defeated, and we actually have what is essentially like a Newtonian fluid when we're under vibration. Why is this important? Because vibration is going to be how we consolidate the material, and it's the period of time that is of concern today that we're thinking about when air bubbles are moving and rising through the material. So here's a picture of how we measure rheology of concrete, and this is some data that shows this kind of Bingham behavior, and we have little tools in the lab that allow us to measure rheological properties on bulk concrete samples. The theory for bubble rise goes something like this, that if we have a bubble with a, it's hollow inside, so there's a buoyancy factor, it's going to be counteracted by Stokes' drag force. And the equations we get from this analysis of the buoyant force versus Stokes' drag force leads us to understand that small bubbles, and it's resisted by the viscosity of the fluid, the smallest bubbles are most slow in their movement. So the velocity of the bubbles U is going to be highest when the diameter of the bubbles are high. And so we get a picture here that under vibration, the first thing that's going to leave the system are the largest voids. They will tend to escape quite quickly. The very, very finest voids have some stability by nature of the viscosity of the system. And so we wanted to see how this worked, and we were able to do experiments of concrete under vibration with air entrainment. So we did these kind of tests by putting an air meter with concrete sample on a vibration table. And we did these tests with concrete, and we could see air decreasing with time. So vibration time is on the x-axis, the air contents on the y, and you see this drop as with time of vibration for concrete. And if you did it with mortar, that is just the paste and the sand, the fine aggregate, we see the same kind of drop. But if you do a test on just paste alone, that's air-entrained, you see almost no loss of air when it's vibrated. Well, that's interesting, isn't it? Something about the presence of aggregate in concrete and mortar, the lack of aggregate when we're working with paste, makes a big difference. And that leads us to sort of think about the granularity of these materials. And so this is another picture where we did some tests where we were able to do a sweep of viscosity or the behavior with a rheometer, and we could do this with different size aggregates, and we could see that when we have the light dim symbols are when we don't have vibration, and when we turn on vibration, our sweep indicates we have this very different kind of drop in yield stress at the slow strain rates. So we know that the aggregates have a pretty important part to play in this problem. And it brings in some ideas about modeling the fluid as a granular fluid. And we have some tools available to us from literature. And none of these things had ever been really applied to concrete materials. These models had, especially in the context of air, looking at air and vibration, we were bringing these kind of things in for the first time. So it was very interesting to see if this would help us explain the behaviors that we were seeing. And so we've got these models, one of which is called the Roscoe's equation, and it gives us the ability to put in volumetric presence of sand and aggregate and so forth. And we can use the same kind of model to put in coarse aggregate for the concrete and so forth. And it gives us essentially the right type of model, the right kind of constitutive performance that we were looking for. So this was always encouraging and led us to move on and see that the granularity of concrete was a very big part of the behavior we were observing. One of the things we saw in our experiments is that this is an experiment that you see here where we have a surrogate fluid. It's a clear fluid that is a yield stress fluid with aggregate in it, clear glass beads. And these little black dots were originally lined up at the top of the sample. These are little steel balls. And they were stable when the sample was not being vibrated. When we vibrate this, that is, the vibration probe turns on, these balls start to sink and drift downward. And you can see that the ones closest to the vibration fell quite far. The ones far from the vibration did not drop at all. So there was this zone of influence where the balls drifted downward because the yield stress was defeated in this material and the gravitational pull could draw that ball to drop. But it didn't last forever. There's sort of a dissipation zone. The other thing you see is that not all these balls were treated the same. This vibration rod is moving back and forth, but the ones close came in were more dramatically affected. And this led us to coin this phrase of cone of action. Now, if you're a concrete technology person, you would recognize the term radius of action. You put a vibration probe into concrete and you see a radius of action that gets fluidized. And we recognized pretty soon that this was a misnomer of sorts. We were seeing it as a cone of action only because we're looking only at the surface. If we were able to look all the way down, we would recognize that was not a radius, a cylinder of action, but in fact was more of a cone of action. And it changes pretty significantly how we think about consolidation and the propagation of vibration through these systems. It also then led us to be able to model these systems, and now we can have models that have no vibration versus, well, the model predicts the no vibration case, and then we go to 2 minutes of vibration. We start with a certain distribution of air bubbles, we apply vibration, we get another distribution of air bubbles. With these kind of tools, you could design the kind of properties you need in the concrete and the kind of intended distribution of air bubbles you want to give yourself freeze-thaw protection. We were able to do simulations where we see these small air bubbles, starting with the large air bubbles. After 300 seconds, here's another picture of microstructure, and after double that length of time, even more reduction of the size that you see here. And this chart tells us how viscosity plays a role here, that when we have very low viscosity, the timing has to be very, very short. If you have very low viscosity in your materials, you run into air loss here of a 99% air loss within a few seconds if your viscosity was very, very low. So anyway, we got our hands around this whole technical problem about the physics of that problem. And we did experiments on how vibration is damped by using accelerometers at different points along a beam that was vibrated at the end. And so we could see that kind of behavior as well, and that became part of our understanding of how vibration is propagated through concrete. Another thing we were able to do in those kind of experiments is measure the air loss at different points using our image analysis technique. And the point that we want to make on this chart is that, again, the paste samples that were vibrated have essentially the same air before and after vibration, but concrete before vibration is about 10% air, after vibration about 5% air, and so this same result is being expressed there. We also had a chance to go to the plant. Actually, KSU students were involved in these plant visits, 1 month stay for 2 plants and 4 days for a 3rd plant. And all these different kind of properties were being measured. We had a chance to deal with plants with different type of vibrator systems on their equipment, rods on the casting machine, vibrators under forms. One plant used a handheld vibrator, and the results, of course, were different in these cases. That was part of our detailed analysis. You can see here a little more how we attach our accelerometer to the equipment, so we get a sense of what is the difference of the acceleration being felt by the material versus being felt by the forms themselves. So one thing that was basically important here is that we confirmed that the handling and vibration of concrete drives air from the concrete in all these different plants. So we have plant A is the blue, plant B is the orange, plant C is the gray, and all of these cases from the left to the right, at the mixer, before vibration, after vibration, you see this tendency to lose air at these different steps of the process. The next idea that we want to then think about is the field conditions of concrete. And we had a chance to have a field testing program at Lytton, British Columbia, as well as here in Rantoul, measuring the temperature and internal relative humidity inside the concrete ties. We used little teeny sensors that measure temperature and relative humidity. We cast these inside concrete ties, shipped them out to the field. You can see here the kind of trees that were established so we could get depth-wise sensitivity to the change of properties. And we installed these in track and then at Rantoul in ballast that was in boxes, as much of a replication as possible of the kind of conditions that we get in the field. So all this data helped us build models about the temperature that you measure inside ties, the moisture that you expect inside ties, compare it to the ambient conditions. We'll always be able to get weather station data. How does the weather station data, how can it be used as a predictor of what goes on inside a tie with different kind of moisture events, precipitation, temperature, and so forth? So we have all these temperature histories, we have all this moisture history, and it leads us to this function, or this is the experimental record, of when we were getting freezing events under saturated conditions inside ties. So you see the top line here is the freezing events of ambient conditions, just the temperature data. How often did we go through a freezing event? And these next ones are how often different points of the of the tie, how often did the tie itself feel this at different depths inside the tie. And so this one's closest to the skin, and these are most interior to the concrete tie. And so this gives us this basic finding that concrete is persistently high moisture during the winter times. Concrete temperatures do experience significant cycling, and we see about a relationship between the weather station versus what the tie feels of about 0.7. So 70% of the time that your weather station data says I've undergone a freeze-thaw cycle, the tie material itself feels it. Otherwise, there's sort of a damping of those kind of things. So this tells us that we receive maybe, let's just guess, 70 freeze-thaw cycles a year. And you might recall that the C666 test requires 300 cycles for its torture test. So actually, this is within a few years, you've achieved those kind of numbers of cycles. And therefore, maybe you might feel that that is, in fact, appropriate kind of testing to assess to this material. Another part of this was how should we sample concrete ties? Right now, they are required to take samples out of the concrete tie itself by saw cutting in many cases. And it's a pre-stressed element, and there's concern about, well, you know, you have these strands inside there, and you're cutting through the strands, and there's a material under stress that you're now alleviating that stress. What does this all mean in terms of measuring freeze-thaw performance? So there was an extensive freeze-thaw testing program in this project. You see here, we tested full-length ties inside the special manufactured freeze-thaw chamber at Kansas State. And you could see that we could achieve the kind of distress that we would expect with freeze-thaw damage. But I guess I should say, we tested lots of different configurations, full ties, half ties, prisms that were cut from the samples, from ties, and also prisms that were cast with no steel in them. And one of the most important findings is proving that anything cut from a precast member that involves cutting through the steel is problematic. We routinely saw worse kind of performance in these saw-cut samples than we did in some of the related half-tie samples. Here we saw some problems as well, but much quicker decay of the freeze-thaw performance in the saw-cut samples. So there's a breezy overview of the kind of things we looked at in this project, and here is a summary of some of the basic accomplishments of the work. The first thing is that we developed new models for vibration and air. These fundamental models, physical models, fluid mechanics models, are some of the first time that we've had that level of detail applied to concrete materials. I think of that as a very important advance. Number two is we documented true field conditions of concrete cross ties. This was something people just speculated about before our project. Now we have real data about that. The third bullet is we proposed new guidelines for making durable concrete. All this kind of information was driven by industry concerns. We wanted to make sure this project spoke to those concerns. And so the conclusions were translated into the idea of guidelines, how to do best practices for concrete production in a plant like that makes concrete cross ties. A fourth one is we propose new approaches for specification language. How should you go about setting requirements for air or testing requirements for air? What would be the kind of specification provisions that would get the job done? Those came out of our project as well. And the last thing is we recommended quality control approaches that would assure this. And part of this is as simple as stop paying attention to some things you've learned in this industry are important, such as the diminishing bug holes. It tends to be a preoccupation with the aesthetic surface quality. It has nothing to do with freeze-thaw durability. These bug holes are not important, and there's sort of a red herring to be focused on things like that. So we wanted to give a new kind of sense of what the parameters are that need to be looked at. And then last, we feel that there's a better understanding of the distress mechanisms, and with that, it leads us to improved product performance. Thank you very much.
So as I mentioned, Professor Lange needs to depart for class soon, but he can stick around for a few minutes to take questions, and I
Been
believe
keeping my eye on it. I've got 5 minutes at least here.
Dan will take over if there's still questions when.
Oh, I think he's got a 1 o'clock thing
Oh,
as
he
well.
does too.
Okay,
So all right, we're going to have to do this fast then.
Fun presentation. My specific question is, do the models that you've developed, do those only apply towards the mix design that you worked with, or is this concrete independent?
I would say it's concrete independent. There's, we encountered a good range of mixed designs. We had 3 plants we were working at. They weren't all the same mixed design. The lab materials we did were even different yet. So the models are not that confined to a specific tailored mix. And we tried to build these models on good theoretical foundation. And when you do that, just as a kind of a broad thing to mention to students doing research, when you're able to do that, you're able to generalize your result. It's very important to try to build it on good principles so that you can generalize your results. If you find experiments that are just using empirical relationships, you may find yourself backed into a corner where there's very little ability to predict another case. But in this kind of work, I think we can predict other cases. Go ahead, Conrad.
Yeah, the next to last slide indicated that the freeze-thaw performance for Sawcut sampling was worse than non-Sawcut. Do you then extend that to say ties that are long line construction where they are Sawcut are going to be less performance for freeze-thaw than a carousel?
I think it's fair to suspect that that's the case. We did not prove that case or take a lot of data on that case, but it's definitely part of our understanding of what happens when we release stresses during saw cutting, and it's part of the story about making sure that we have, understand that the degree to which we have stresses developing in that transfer length zone, the timing of the saw cutting, what's the strength of the concrete matrix at that time. It is complex. People involved in this have been pondering all these kind of things for a while. I don't think that we know the end of the story. Will?
Going back to your result that showed that you have different vibrational performance with whether or not there's aggregate present.
Right.
Is there a dependency on vibrational frequency there?
We did some testing on vibration frequency, and there, in the boundary conditions, of course there is. You move your frequencies to very long periods. Of course you're changing things dramatically. Within the normal ranges that you expect to see in industry, we did not see a great amount of sensitivity. I think that these lessons we're learning are broad and general for industry. And I think there's boundaries to it that if you keep looking to farther and farther out in this spectrum, you will see an impact. But we weren't drawn to think of that as a major thing. One of our recommendations is not a specific frequency that this is the magic one. No, we don't have that.
Thank you.
Yeah.
So my question is very related in that since you do see different behavior in air entrainment with aggregates, what kind of recommendations are given in regard to aggregate choice in concretes?
Well, a lot of our comments about aggregate choice have to do with making very sure that you really do know what that is. I mean, this is actually somewhat standard for concrete technology to have done sufficient and adequate freeze-thaw testing of your aggregate. So you want these problems to be certainly not brought in like decracking problems. We don't want that to be a concern for us. We do have some insight about size. When you go to those equations, you'll see that diameter and size is a parameter in some of the granularity models. So we could look and you could tune the response that you intend to get by looking at your sizes of choice and so forth.
You had indicated that you had given some guidelines for making durable concrete. Were one of those an adjustment in the amount of entrained air, say, that was measured at when it was plastic, so that you have residual air when it's hardened that's sufficient?
Yes, that's a good way to put it, in fact. So the question is about, is one of these to talk about how to properly overshoot air entrainment values so that you can accommodate the losses. And that is true. That is one of the kind of recommendations we have. A second one that goes along with it is a better knowledge of what is the size distribution you're actually creating. I would say that most plants have no clue. They don't measure it that specifically in that detailed way to know about what would be the difference between this air entraining admixture versus this air entraining admixture, and how my mixing speed changes the size distribution, et cetera, et cetera. All these processes make a difference.
I just seen a presentation recently, Tyler Lange.
Yes, yeah, I know Tyler.
Super air meter, and how in addition to quantity of air, gives you feedback as to the quality of that air.
Okay, the comment for those online was about a researcher at Oklahoma State named Tyler Lange, who's giving some attention to this idea of the quality of air, and he is looking at those kind of features. Is it the right type of air, meaning the population is in small bubbles? Right. Good comment, thank you. Well, thank you all very much. I think I'm going to kind of wrap up here, and I'll turn the floor back over to Chris to make any kind of conclusion you need.
Well, just to thank you very much. I appreciate very much this interesting seminar, obviously highly pertinent not only to the research program that's going on here, but also the rail industry in general. And for those of you who didn't get to ask questions, Professor Lange is in the building, and so I will suggest you make an appointment with him and follow up. The one last sort of housekeeping item is if anybody didn't sign the attendance sheet and also did not swipe in, if you could do that. Otherwise, I think we're finished. So thanks very much. Oh, I know one more thing. Yes, there will be another Hay seminar in 2 weeks. David Davis from the Transportation Technology Center will be talking about some of the research they've been doing on advanced railroad track turnout design. So that should be very interesting.